All right, let's work this problem. This is Mas-Colell Winston Green 1.4D. So the text says this is related to plot 1973. Okay, I don't know what that is, but maybe it's relevant. Okay, so it says show that a choice structure, this is a set of budgets with a choice function for which a rationalizing preference relation exists, satisfies a path invariance property for every pair of budget sets, such that the union of those pairs is also a budget set, and the union of your choices from those budget sets is also a budget set. We have that the choice from the union is equal to the choice from the budget sets. Thus, the decision problem can be safely divided. Okay, I think I see. All right, so it says like basically, suppose we have a set like this, A, B, C, D, E, F, and we break that down into A, B, C, and D, E, and F. Okay, I'm actually nothing about this says they have to be disjoint, but let's just say like, okay, the union has to be the grand set. So it says like take a menu and then break it down in any way. Your choice from the union, A, B, C, D, E, F, forgot the C, yeah? Let's say that's A. That has to be the same as if you chose from the your favorite things from these. Okay, and let's say that's like ABC, your favorite thing is A, or D there, yeah. Your favorite thing is A, and your choice from D, E, and F, right? Let's say your favorite thing is D. Then if you chose from your favorite of those things, that's A and D, that also has to be A, right? So like your choice from the whole menu is the same as your choice from your favorite thing of any way of breaking down that menu into submenus. All right, that's what we're trying to prove here. All right, let's do this. So, okay, we have to prove this. This is like a set equality. Like this set is equal to that set. So we have two goals. We have to show, like for two sets to be equal, we have to show that anything in this set, let's say like if X is in that set, then it also has to be in this set. Yeah. And then our goal two is to show the reverse. Like if X is in that set, then X is in this set. All right, let's try this one first. So if it's your choice from the full menu, then it has to be one of these. Okay. How do we want to do that? Okay, so first of all, X is in the choice set from B1 cup B2 if and only if X is at least as good as Y for all Y in B1 cup B2. All right, yeah, there we go. Okay, that's like the definition of it being a choice. And then let's just show that, well, that means it has to be as good as anything that could be here. Like anything that is um, in your choice from B1 and B2 also has to be in the union of B1, B2. Okay, so let's do this. For any Z in that, either Z is a choice from 1 or Z is a choice from B2. This implies, right, since like your choice, if you're a choice from B1, you have to be in B1. If you're a choice from B2, you have to be in B2. This implies that Z is in B1 or Z is in B2. And thus, Z is an element of B1 cup B2. Right? Okay, so now we have like, yeah, and then we're done, right? So like, um, so now we have since any Z, since any Z in the union of the choice from B1, B2 is in B1 cup B2, and X is at least as good as Z, or like any Y, X is at least as good as Y, for any Y in B1 cup B2, then X has to be at least as good as Z for any Z in, this is feeling a little redundant, but I think you get the idea, right? Like any z in that thing as well. Right, and then we're done. We're done. We've closed that goal. Okay, now we move on to the next one. Okay, yeah, again, like I'm gonna, there's this, like a little bit of redundancy there, but I think the logic is right. Okay, now we show that if we have, this is probably the harder direction. If you're in the choice, if you're in the union of the choices, then you're in this. Okay, so I think we probably need transitivity here. So like, let's say, suppose we have a z in B1 cup B2, then z is in B1 or z is in B2. Let y, let's just suppose without loss, we can just call it bi. Yeah, okay. So let's call it bi. Let bi be the set, be one of the set is it's in. One of these sets it is in. No, we could just let it be b. Yeah, let's call it b. Whatever, leave it, we'll leave it. Okay, let y be the element, an element of the choice from bi. Then y has to be at least as good as z. Okay, so what we found is we know that for any z in, where are we? What am I trying to prove? Yeah, okay, so for any z in this thing, there has to be some y that's at least as good as it. Basically, like we'll just pick this thing, right? Like we'll pick the choice from B1, right? So we'll let the choice be that. Then that y has to be at least as good as z. And we know since x is in the choice from those things, then x has to be at least as good as that y, right? Like, so x has, since y is an element of one of these choices, x has to be at least as good as y because x is one of the best things in that choices. And so then by transitivity, x has to be at least as good as z for any z in the union of B1 cup B2. I said it was harder, but I don't know. It felt easier actually in the end, except we had to leverage transitivity here. Okay, so I think that's it. I think that covers both of our goals. Yeah, nice.